Okay, so this is a solution to 1610. So it says show that the fractional change in the speed of sound dv dv. So this is the change in the speed divided by the change by the speed for due to very small temperature change dt is given by 1/2 dt over t. And it says, hint, start with equation 1610. So I guess B is figure out what the result is. So let's look at 1610. I'm thinking it's the one where it's the square root of t over 273. But yeah, what they're saying here is the speed of sound is equal to the square root of gamma, which is ratio of specific heats times R times T divided by M. So we didn't talk about that in regular class. We said V was equal to the square root of T divided by 273 times 331. So all this stuff, so this is 273. This is the absolute temperature. And so the question, where does 273 come into that play? I don't know. It probably relates to this part. So the standard temperature is used to calculate the speed. Anyway, we probably can use either one of those to do it. So if you think about what we're going to do is we're going to, what are we going to do? That's the good question. So from a differential standpoint, you know, if we said dV, and then you take the derivative of this with respect to t, so all this other stuff, the square root of gamma r over m, and then we take the derivative of the square root of t, and the derivative of the square root of t is going to be, well, you put it in a fractional exponent term, so it becomes 1/2 times the square root of t in the denominator. So it's like taking the square root of x. It's 1/2 square root of x. And then you put a little dt on the end, this differential thing, like that. So I think what I'm thinking is that, you know, if we divide both sides by v, so we'll get dv over v here, and at the right-hand side, we can use this original expression. So we'd have dt, we'd have this part. So that's equal to 1/2 1 over the square root of t times dt. And we divide that by, well, we forgot this other expression. We forgot this little bit there, which is the square root of gamma r over m. And we have that same little bit, the square root of gamma r over m, in the original expression on the right-hand side. And then we have the square root of t. So all I'm doing is taking this, and I'm separating the square root of t from that. So what'll happen is these things cancel out. And then you have 1/2 times the square root of t, but what we can do is write that as square root of t over 1. So if we take the reciprocal of that, that's 1 over the square root of t, and then times dt. So we get dv over v is equal to 1/2 times 1 over t times dt. And that is the expression we're looking for. So that's kind of how that shakes out. Okay, so the second part of the problem, was asking the question, the speed of sound in air is 20 degrees C, so V is 344 meters per second at T equals 20 degrees. Use the results in part A to find the change in speed of sound for 1 degree change in air temperature. So dt in this case is 1 degree C. Now we want to make sure we use the absolute temperature here. So T is equal to 293 Kelvin. So if we solve for dV, that's the change in the speed of sound. We multiply both sides by V, so we get 1/2 times 1 over T times dt, and the whole thing times V. So we get the change in velocity, speed of sound is 1/2 times 1 over the absolute temperature, which is 293. Now the dt is, whether it's Kelvin or degrees C, it's the same thing, so it's 1 degree. dt is 1 degree C. And times the speed of sound, which is 344 meters per second. So if we solve for dV, by plugging in the numbers, we get 0.5, 1/2, divided by 293, times 1, times 344, and I get the change in speed is 0.587 meters per second. And let's just check that out. So if I were to do, say, 294 Kelvin, and I used our thing that we learned in class, which is the speed of sound is 331 times the square root of T over 273. So let's use the initial temperature, which is 20 degrees, so that's 293 over 273. See how closely that comes to their number, 344. So 293 divided by 273, take the square root of that, times 331. Oh, well, no, something's wrong there. Forgot to times that. So 1.0, let's fix that. Let's do it again. 331 times the square root of 293 divided by 273, and I get 343. Okay, so those are not exactly the same. So, but since I'm using this equation to predict how much change it is, if I go to 294, then the speed is 331 times the square root of T, which is 294 over 273. So let's plug that in there. And I get 343.5 meters per second. This one's actually, if I save an extra decimal point, is 342.9. And if I subtract these two, 343.5 minus 342.9, I get 0.6 versus 0.587. So you can see it actually comes out pretty close using this differential form to predict the change in temperature versus using the equation.